Okay, let's continue with discussion of representation of X. So this is a definition for any system. Yes, of course, we always consider unital system algebras. So it's a unital system algebra. A representation let pi and pi from A to B of H be a unital star representation. So when I say representation, it is unital star. A vector xi in H is said to be cyclic. A vector is said to be a cyclic vector. Cyclic if you apply this pi of x, x coming from A on this xi, that will give a vector subspace of this. You take the closure. I mean, if it is not, you have to take span closure, but this is linear. So you take the closure in the Hilbert space now. That is equal to 4 of x. So if the xi acted upon pi of x for all x in A, if it generates the whole of x, that is called a cyclic vector. And the representation pi is called cyclic representation. A representation is cyclic if it admits a cyclic vector. Cyclic vector is just you take a vector xi at pi of x for all x, then take the closure. Okay, you take the closure in the Hilbert space now. That is whole of Hilbert space. Okay, that's called a cyclic vector. If a representation admits a cyclic vector, then it's called a cyclic representation. So, example. Okay, maybe I define it that x. X is a compact. Let's say that x is compact. For our purpose, you can assume it's metric space. That's not needed. You can assume metric space. You don't want any complication. So it is a finite vector space. X is compact and mu is a finite measure on this. Define by the representation depending on mu from C of x to B of L to x. Of course, the only Hilbert space we can construct out of a measure space is L2. I mean, only Hilbert space we can construct out of a measure space is L2. Okay. So for each pi mu is a representation of C of x on this defined by the following. Pi mu, which is just multiplication operator of F acting on G equal to Ft for all F in C of x, G in H. We define it. Then we claim then pi mu, then it's not there. Pi mu is a cyclic. I mean, you have to verify it's a representation to start with. Cyclic representation with cyclic vector. This constant function. It's not identity. I mean, it's not the identity polynomial. G of t equal to t. It is a constant function 1. I mean, constant function 1 is in L2 because it's a finite measure, right? Which is in L2. It's a finite measure. The constant function is integrable, and that is in L2. Okay. So it is a constant function is the cyclic vector for this. So let's first verify that it's a representation. First, clearly it's linear. The pi mu is linear. Pi mu of Fg. Of course, you apply G first and F later, and it's going to be multiplication. So these things are clear. So, and it's unital. So 1 is 1. And pi mu of F, I want to verify the star. Pi mu of F for F in G of X, G in L2. Okay. I take F in G of X and G in L2, pi of F acting on G and H. G and H. This is equal to now this is equal to, I just write the inner product. I mean, explicitly write the inner product. This is L2 inner product. So this is going to be G H bar. Right? This is the inner product. And this is equal to integral over F. G bar H bar, which is equal to inner product of F with, sorry, H, yeah. No, sorry, F bar. I take the, sorry. It's all commutative. It's all functions. Fg H bar. This is equal to integral over F. F is, I mean, it's commute. So it is G F bar H bar. I just written the same thing. Which is equal to inner product of G with pi of F bar H. And this implies pi of F star with pi of F bar. Okay, this is how we verify this. I forgot. It's, I mean, we should have first verified that. Sorry. First thing to verify is pi mu is bounded. I'm sorry. Pi mu of F acting on G L2 norm is less than or equal to norm F infinity. I mean, it will be an integral where the, I mean, the F will be, I mean, if you take the square of this, that will be integral of this, and you will have a F square, mod F square will be there, and mod G square will be there. You can take out this. Okay. Okay. So this implies pi mu of F is bounded. Norm of this is less than or equal to norm. Okay. This is what I should verify for all F and C of X, G in L2. First, I should have verified this. For each, I mean, for F, pi mu of F is a bounded operator. This shows it's a bounded operator, so it lands up in G of H, G of that. Then it satisfies its respect to multiplication, star, unital, everything. So it's a representation. And all this is implies that pi mu is a representation. So this is a multiplication representation. When given a measure, we can define this representation. And so one is in L2. C of X, all C of X is in L2. Okay. All C of X is bounded functions and they are integrable. Okay. Now pi of C of X acting on whatever I called it as G naught. G naught is the one function, is equal to C of X. But this is dense in L2. Do you know this? Was it proved? C of X is del 2x if X is compact. Dense in all LP except L infinity. Except P equal to infinity. It's in all the Banach spaces, it is dense. You know this. You know the proof. One has to go through the regularity of the measure. Okay. I mean, you want to approximate any functions here, let me orally tell you. You want to approximate any function here, it's enough to approximate any simple function. Okay, and so it's enough to approximate any the characteristic function. You call characteristic function or indicator function. Characteristic function. Okay, in ISI they call it, I mean, statistics oriented. From ISI we call it indicator function. So if you have to enough to approximate any indicator function, so if you want to apply this 1E, then any measure on a compact metric space is regular. We have done that, I believe. So because of that, you can find E, you can find a compact K, and you have a open U, something such that mu of U minus E is less than epsilon. Now, Urisan lemma, you get a function which is takes 1 here and 0 here. Now you integrate it and find that you will get 1 minus some. You can prove using this, you can prove that the difference is, the L2 difference is less than epsilon something, epsilon or something. Okay, so it's because of C of x is dense here, this is true. So this is a cyclic representation. Okay. Now let us use the Riesz representation theorem, which to prove the following. Let pi from C of x to some B of h is a cyclic representation. Then there exists a mu finite measure on x. Whenever we say a measure on x, it is defined on the Borel sigma algebra. Okay? You have the, I mean, whenever we talk about metric space, we have the open sets, we take the sigma algebra generated by the open set, which is called the Borel sigma algebra, and our measures are defined on that. Okay? That's what we use. Okay? So then there exists a mu finite measure on x and unitary operator from L2 of x mu to this h, such that u star pi mu u, I mean, it is unitary. Any cyclic representation is unitarily equivalent to a representation given by a measure. That's what this is, equal to pi. Any cyclic representation of C of x is unitarily equivalent to a representation given by a measure. It can be represented as multiplication operators on. That's what this is. So proof. So let xi naught, I mean, we have pi defined from that. Let xi naught in H be the cyclic vector, be a cyclic vector. That's not B, cyclic vector for pi. Define P of f equal to pi of f xi naught, xi naught. Okay. P is a function from C of x to complex number, right? I define phi of f. I take pi of f, which is linear. F going to pi of f is linear, and this is just another product. So this is a linear functional, okay? And you can prove it's bounded from the boundedness of pi, okay? But that's not needed. Positive linear function is enough, okay? And pi of, if f is greater than or equal to 0, a function greater than or equal to 0, then pi of f equal to pi of f xi naught, which is equal to pi of f power half pi of f power half. Okay. I mean, it's a positive function, so I take the square root, and it is positive function, so its bar is same, so it's self-adjoint. So this is equal to pi of f power half xi naught, pi of f power half xi naught, and which is equal to norm of pi of f naught power f power half xi naught square greater than or equal to 0. Okay. So this linear function, so phi is a positive linear function. P is in A star, I mean C of X star, positive. So there exists a positive measure mu such that P of F equal to integral over X F dV. This is Rees representation. It follows from Rees representation. Now we want to define the unitary operator and see that pi and pi mu are intertwined by that unitary operator. That's what we have to see. So you define okay, so actually we don't need, but to check the well-definedness, we may. I will tell you a lemma. That lemma is more general. It's for a total set, but maybe I will tell you that lemma. Here we don't need it, but it's better to record this lemma and invoke it whenever it's not. So we have two Hilbert space, H1 and H2. Yes, and S contained in H1, the total set. I'll tell you what it means. Total set, that is, we take the span, closure of S is equal to H. That's what it means by total set. Dense set means closure is H. Total means you take the span and then take the closure. That is a total set. And suppose U naught be a function, some function. It's a, I'm not saying there is no linear structure here. Some function from S to. Okay, so it's better I give you it as an assignment, first assignment. So S to H2, okay, is that naught of X, naught of Y equal to XY. I'm not assuming anything. I'm not even assuming I'm just saying some function. Okay. Then there exists a unique, well-defined isometry. This is U naught, sorry. Isometry U from H1 to H2 such that U restricted to S is equal to that U naught. So if it satisfies this condition, you don't have to worry about it. It's automatically well defined. And it's isometry. It preserves the norm. And it will preserve in the, using, it's defined on S. So you have to extend it to the span, natural way, by linearity. And you have to check that it is well defined using that. But it will preserve the norm. So it will be well defined and isometry also. So because it's an isometry, it preserves the norm. It's isometry, so it extends to the whole space. Okay, something preserves the norm, something bounded will extend. Something bounded on a total set will not extend. Okay. Something which preserves the inner, something even preserves the norm on this will not extend. These are other things. Suppose if you have a linear operator from H1 to some dense subspace to dense subspace, which preserves the norm, then it will preserve the inner product. Something defined on a linear space which preserves the norm will preserve the inner product. But then something which preserves the norm and a total set need not preserve the inner product. Okay, so that something need not be even bounded. Something may preserve the norm. I have encountered examples where something preserves the norm and a total set, but still it will not be bounded even. But if it preserves the inner product, then you can extend it to an isometric. Okay? And U is unitary if and only if U of S is total in H2, which is clear, of course. It has to be on to, so it's total in H2. Okay? This is assignment. Okay? Better you write it and get convinced. But here we are not dealing with total subset, it's a subspace, but still it's better to invoke this. So now define U, maybe from, I will say, U of phi of F. What is the cyclic vector? G naught. G naught. You define pi mu of, no, pi mu of 1. C of x is contained. So pi of F, U of F, U naught of F is equal to, of course, U naught of pi of F of 1. Okay, the function 1, right? And I'm just taking a multiplication. Okay, I'm trying to define something from L2 to H. Okay, U naught of F equal to pi. This is of F of G naught. Okay, what is an operator from pi of C of x an operator from pi of C of x to H, course, okay, which I defined on this U naught of pi mu of C of x. Okay. Pi mu of C of x, sorry, 1. I mean, which is the same as pi mu of just function. I mean, I'm acting on 1, you will get the function only just to square it. So this is an L2 of x. Okay. This to here, I just define it to be, I take pi mu of f to pi of fg. That's all. Then I verify this, pi mu of f 1, pi mu of g 1. Okay. That is equal to integral, just write this is L2. Okay, L2 in the product. This inner product is L2 inner product. Okay. That is equal to integral fg bar, that's all. Right? Fg bar dv. But this is equal to phi of fg bar dv, phi of fg bar. Yes, that is how we got the mu. Okay. Now this is equal to pi of fg bar. Huh? What is in? G, here. No. Pi, no, I am just very, I'm verifying the other way, sorry. Here you want to put, U naught of f is equal to pi of f g naught. Cyclic vector for h, correct. What is that? Psi naught, okay, sorry. G naught is the one vector, sorry, yeah. I was having that thing, psi naught, sorry. Yeah, this is what it is, psi naught. Psi naught is, sorry, psi naught is a cyclic vector. Now it's okay. Maybe one should go through the, this is okay. I mean, I should have started from what I'm going to write there to here. Yes, that is what we want to verify. You want to verify this, no? You not this equal to this, but I am verifying from here to here. Okay, something wrong. But that's a way of going from verify this is equal to this. Okay? So I'm verifying from, it comes from the bottom. This is equal to xi naught, xi naught. That is how we got the vector. That's how we got the phi. That's how we got the mu. Okay, so, but this is equal to pi of getting phi of f, phi of g, which is equal to f and g, which is equal to fg bar, which is equal to phi of fg bar, maybe phi of fg bar. Why am I getting it flipped? But that's okay. These are commutative, so it's okay. I mean, you can get by bar and you can bring it here because it's commutative. It's okay. Which is phi of f xi naught, phi of g xi naught. That's what we want to verify, right? We erase this. Oh, is okay if I erase it. So, but this is the assignment. Sorry. This is okay now. So we have verified that U naught is the inner product. Okay. I mean, pi of f xi naught, pi of g xi naught. I should have started from here. Pi of f xi naught, pi of g xi naught, which is equal to pi of fg bar. Okay, and that is equal to, that's how the entire phi is defined, which is equal to this, which is equal to, that's how we got the mu, so which is equal to this, and that is by definition it is equal to this. So this implies that it's a unitary, and it's clear and clearly by mu of x. Maybe that's called G naught. No? G naught is dense in H. Okay, so there exists a unitary from L to mu, L to H to H, such that pi of, sorry, u of satisfying pi of f at G naught. G naught is a one function. Okay, G naught of one. G naught is a reducible one. It's that function equal to pi of f xi naught. Okay. Now you can verify that u star is the inverse. Okay. And it will u star of pi mu of f u acting on any pi, I mean, it has to act here, pi of f xi naught. Here f is there, so g xi naught equal to pi of f, pi of g xi naught. Okay. So since this pi of g xi naught, I mean, we are using all this argument. That's why I'm listing it out. I mean, I have defined a unitary operator. I got a unit, something preserves the inner product, so I got a unitary operator. Okay. Now on a dense subspace, this is an operator. U star, this is an operator. U star, this. This operator acting on this is a vector, use this. Okay. So this says that u star pi mu of f, actually u pi mu of f, u star equal to pi of f on pi of c of x g naught, xi naught, which is dense. Okay. Which is dense in H. So this implies u of pi mu of f u star equal to pi of f for all, because as operators they coincide on a dense subspace, so they have to be equal. Okay. So they are continuous, so they have to be equal for all f and c. And we have to actually go through all these arguments. So that is how. So we got the u. Okay. This is clear now why I am doing. Okay. I define a unitary operator. I mean, I'm repeating the same thing, but that is how it is defined. Okay. We have a dense subspace. generated by this representation acting on the cyclic vector. You act the representation on the cyclic vector, that gives define the dense subspace. On the dense subspace, I take pi mu of f going to pi of f, basically. That's what I do. That gives a unitary operator. Now I verify that unitary operator intertwines these two representations. How do I verify? I act it again on the dense subspace, and I get this relation. Okay, this is satisfied on a dense subspace. So it has to be. Okay. We have no doubt. We go to the next topic. Every cyclic representation will be given by a measure. That's what this says. And it can be represented as multiplication operator. C of x, the representations, cyclic representation. See, the idea is this. We want to determine all representation of C of x. So by Zorn's lemma, we will deduce that any representation can be written as countable direct sum of cyclic representation. Okay. And each cyclic representation that we use Zorn's lemma, that's the direct application of Zorn's lemma. And any cyclic representation is given by a multiplication. Is a multiplication. So it will be direct sum of countable measures. You have to take different, x naught or something. You take disjoint union. Direct sum of L2 is something like you take the disjoint union of sets with measures supported on that. Okay. So that is the idea. So further, the first step is we have proved that any cyclic representation is actually a multiplication. Now we want to prove spectral theorem. For that, it's not C of x is not enough. We have to consider representation of L infinity. Okay. So, have you done convergence in measure theory? It's okay. No means I will do. It's most probably not. No. But you have done other things. But L infinity you have done. L infinity is a Banach space. All those things proved. Okay. So, L infinity, x mu. Mu is a finite measure. For us, mu is a finite measure. We can assume it's a finite measure in a compact metric. Okay. On compact metric space. It is not needed, but that's okay. We are only going to use spectrum, the sigma of a normal operator as x. Well, we will use C, but still the measure will be supported on a compact subset. Okay. Now you define, go through one by one. Pi mu tilde from L infinity. This is also a C-star algebra. This is a C-star algebra with bar, and it satisfies the C-star identity. Fg is just the basic property of infimum and supremum. Okay. So you define pi mu of L2 x mu to L2 of x mu, the same L2 of x mu. Same representation. Pi mu of pi tilde mu of f acting on any g is just f, multiplication. Take the same multiplication of we have the same argument which we use for C of x will show that this is a representation. There's no difference, the same argument. But this will be something more. Proposition. Pi mu tilde is a isometric representation of L infinity. That is pi mu tilde of f norm, this is operator norm, is equal to norm f infinity. Here I use the same thing. See that this is not correct actually. See in real line with the Lebesgue measure, the L infinity norm and C of x norm, uniform norm are same. But when you have a measure, it may be different. Okay, so it's L infinity norm. By infinity, I say the uniform norm of C infinity. It's not true that the C of x norm, infinity norm, is same as L infinity norm for a continuous function. Continuous function is of course bounded, so it is in L infinity. It will be this way, right? This will be less than this, right? Because how is infinity norm is defined? L infinity norm is infimum. L infinity means there exists a subset of measure 0. Outside that subset is bounded. That is what L infinity is. Okay, so L infinity norm is infimum of k such that f of t is less than or equal to k, and there exists a subset E with mu of E equals 0, and f of t is less than or equal to k. Okay, there exists a measure 0 subset. You remove that measure 0 subset. Outside that, it's bounded. And you are taking infimum of all those cases, okay, all such cases. That is the L infinity norm. But here you have on the whole set, it is bounded by something. Okay, so that will be bigger than this. Okay, this is this is bigger than this. So L infinity norm is less than the C of x norm. Okay? And they will be equal in some cases. That depends on the measure. Okay? That is indeed equal to saying this representation is isometric. Whenever this representation, whenever this representation is isometric for, because this will be, when you restrict this representation to C of x, you get the multiplication representation of C of x, and it should be isometric there. That's what it means. So isometric means it preserves the norm, so it is continuous with respect to that. Further, it satisfies the following. Let Gn is a sequence contained in L infinity with they are uniformly bounded. Uniformly infinity, less than infinity. Okay. And Gn converges to G in L infinity almost everywhere. Okay. Then, I forgot to say this. I will write this and tell you. Pi tilde of mu of Gn converges to pi tilde. Okay, I will just write it. Xi, pi tilde of G xi. Maybe, yeah, xi is fine. Xi is fine. Pi tilde mu xi for all xi in L2 of x mu. This is just because it's L2, I am writing xi. This is what is called strong convergence for whatever the reason. Okay, so I will make the definition here. This says that we have a multiplication representation of L infinity on L2 mu on L2. That representation is isometric, number one. Second, if we have a uniformly bounded sequence, okay, then and Gn converges to G almost everywhere, then pi of Gn converges to pi of Gn converges to pi of G strongly. So what is strong convergence? It's just point-based convergence. Norm convergence is something more. Norm convergence means, if you have a Tn, we have some operators, B of h. Tn is for some h, B of Tn is contained in B of h. Then, of course, norm convergence means the norm of Tn minus T should go to 0, which is stronger. But this will, of course, imply that Tn xi minus T xi, this norm will go to 0. Okay? And this is what is called strong convergence. But is it a topology and all that? If you want, I will tell you what is topology. So define. There is something called, on vector space, something called locally convex topology. Never mind what it is. If for fix, define for xi in H, this is for a general Hilbert space. For xi in H, rho xi, acting on T equal to norm of T. Okay. This rho xi will be a semi-norm. It will accept, it will satisfy all the properties of norm except it's not faithful. I mean, it's a positivity, strictly positivity condition will not be satisfied. Okay. And the topology generated by this semi-norm this is, remember, it's a norm on operators, semi-norm on operators, is what is called a strong topology. We can explain what the strong topology is. So you take this set, Bx for x in for B xi in H, okay, equal to B xi equal to all those T in B of H. This is not needed. We only worry about this convergence. I'm just telling you what the topology is. We don't require all these things, okay? Because this is not a metrizable topology, and you have to use nets and other things. We will not be using it. We only use the sequences. This is just to tell you what that topology is. T in B of H, then norm of T minus some T naught, T xi. So B of some xi and T naught and epsilon. Okay, something given by the T minus T naught xi is less than epsilon. Consider this set. Okay, take finite intersections with different xi naught and different T naught. Maybe this xi naught can be same. I mean, you can actually work with same xi naught, maybe with epsilon also, but you have to use different T naught. I'm not sure. But anyway, take finite intersection and arbitrary unions. That gives a topology. Okay. So this is the base. You take these kind of sets, take finite intersections of this set, finitely many such intersection of such set, that will be the base for the topology. Okay. This topology is generated by this. Okay. This is what is called strong topology. And some net T lambda converges to T strongly is equivalent to saying T lambda xi converges to T xi for all z. Okay. Oops. So the claim is pi mu tilde takes uniformly bounded almost everywhere convergence to strong convergence. Okay. This is something. See, the almost everywhere convergence is not a nice convergence, not given by metric or something. Okay. But still, this happens. So we will use a slightly weaker convergence called convergence with measure. But for that, I need to define it. So I will come to that. Okay. So proof. So we have defined the multiplication representation of L infinity and L2. Okay. And we want to check first, we want to check that it's an isometric. Okay. So clearly, pi mu tilde of F acting on G, norm of L2 is less than or equal to norm of F L infinity times norm of G2. Okay. So norm of pi mu tilde F, this norm is less than or equal to norm of FL. There are, well, in the book we are following, Sundar's book, there is one argument given. I can go through that, but there is a better way of saying that this is actually equal to that. One way is something, okay. So define En. I want to show that it's actually equal. Okay, for that I have to produce a sequence in L2. Okay, where it approaches the norm. Sequence in L2, in the unit ball of L2, where when you apply it, it approaches the norm, actual norm. So define En equal to all those x in x, or t in x maybe, because you want to use x for something else. X t in x such that we are dealing with f now. F of t is greater than or equal to mod of norm of infinity, L infinity, minus 1 by n. Okay. And mu of En is greater than 0. Because norm of f infinity is the infimum of all those k's such that mu of k, mu of k is 0 outside that. Okay. If this is equal to 0, that infimum condition will be violated, right? Okay. Norm of f infinity is the infimum of all those k such that mu is less than this in that. If this is not the case, then f norm of minus 1 by n will be less than, will be the norm, will be less than that. Okay, infimum of this, right? I don't have to go through it. So it's, so if you take if you minus 1 by n, there will be this set, this is a positive measure. Okay, this is positive measure. So En, I take Gn equal to 1 En. This is the characteristic function. Takes values 1 here, outside 0. Okay, and divided by, because we are using L2, I use this mu of En over half. Okay. Then pi mu delta of F acting on Gn L2 norm. So we are using, we are just going to multiply Fgn. Fgn is 1 En, so the integral will be over En only, and we get 1 by mu En. Okay. And it will be multiplied by, sorry, this should be G. This is okay. Yeah, this is okay. This is okay. This is okay. There is no G. G is what we define. Okay. And it takes value 1 here, so you will get only Gn, mod Gn square, right? And here the mu En is square equal to Gn square d mu. This is greater than, maybe you take the square root of that. Okay, and you take the square root of that, which is greater than or equal to mod f infinity minus 1 by n, right? By the definition, on En, Gn is greater than this. Right? So it will be greater than square of this or whatever, you take the square root. This will be greater than, right? Shouldn't that be? Here is. Correct. Gn is 1 on that. Sorry. Yeah, it's here. Good. Okay. So this is for all n, this exists. So this implies pi mu of f delta. This norm is norm f element. You can do the same thing using spectral radius. Maybe I will do that, because it's better to understand what is invertibility and all. Okay. So we have proved the first part. Okay, I will go through the spectral radius argument also, which is actually given in the book. we want to prove that pi mu of G, pi mu of F, this norm. See, notice that all these pi mu of G, all those things are normal operators. G and G bar commutes, and pi mu of G and pi mu of G bar will commute, which is the star. So they are all normal operators. They are commuting. So they are all, I mean, they commute, everything commutes. So it's normal operator. So this is a normal operator. So this is equal to spectral radius of pi mu of F, right? Okay. Spectral radius, gamma. Spectral radius of pi mu delta of F. Why is it equal? Now, okay. So now we want to prove that we I mean, claim. Okay. This is actually equal to spectral radius of F itself in L infinity. I mean, L is C-star algebra. So we have spectral radius for that. Spectral radius of F in L infinity. Okay, as an L infinity. So now this is equal to norm F. Okay. L infinity. F is a commutative C-star algebra, so it's everything is normal. So norm F is equal to spectral radius of F. So we only have to prove spectral radius of this is equal to spectral radius. Okay. So, okay. To prove this, so what is something in the spectrum of the F is in L infinity? What is the spectrum of F? It is all those lambda such that F minus lambda is not invertible in L infinity, right? By definition, right? In the C-star algebra, it's not invertible. That's the definition, right? Okay. So sigma F is this. But that is equal to claim, again claim. This is equal to all those lambda such F, I mean, let me write F in minus lambda is not invertible, is equal to saying F minus lambda is not invertible in L infinity is equivalent to saying mu of this set F minus lambda less than epsilon, okay, is greater than 0 for all. In C of X, what does invertibility mean? If you have, let's look at C of X. Okay. What does invertibility means? It should not be 0, right? So F is in the, for that, I mean, if lambda invertibility means F doesn't vanish. Okay. So that which is lambda is an eigenvalue, lambda is in the spectrum. If F minus lambda is not invertible, that means lambda should be in the range of F. I mean, then only it's not 1 by F, you cannot write. Okay. So this is like kind of essential range, whatever. Okay. This is all those, I mean, this is all those T in X. I mean, when I write it, you are used to this notation, no? When I just write it without, I mean, when I just write the function or something condition, is all those things which satisfies this. F of T minus lambda is less than epsilon is greater than. Okay. So let's show that this is the but this is clear, no? Is it clear? I mean, suppose if it is is it clear? This is suppose I mean, you just have to. So let's go through the other way. I mean, invertibility condition. So suppose mu of t in x such that f of t minus lambda less than epsilon naught. There exists an epsilon naught. Okay, such that this is equal to 0. Okay? Then you can, I mean, outside this set, you can invert it. Okay? Because it's strictly less than epsilon naught, strictly greater than epsilon naught, so you can invert it. Okay? This implies f minus lambda is invertible. Okay? So why is the other way? You see why the other way is true? 1 by 1 by norm of the inverse. So suppose f is invertible, you take the 1 by norm of the f inverse, and what does it mean? Oh, that will be the epsilon, right? 1 by f of lambda minus lambda. You are saying that f of lambda minus lambda. I mean, oh, then you are taking the 1 by norm of that. What is the argument? Sorry, f of t minus lambda. Correct. Yeah. Yeah. I mean, these are all, of course, not functions. They are equivalence classes of functions. So you have to show that I didn't verify it before the class. So I leave it as exercise. You should sit down and verify it. Okay. So this implies that f is not invertible, then this is true. On the other hand, if this is equal to saying this is, I mean, this is equal to that's it. That's what I want to say. This is all those lambdas. I just want to say that this is actually equal to this also. Why? You take this set, let's consider En equal to all those t in x such that f of t minus lambda is less than 1 by n. Okay. Right? Then same idea, Gen equal to 1 by n divided by mu of En power half. The same thing, you call it Gn. Okay. This will give an approximate eigenvector. Okay. But again, the other way I have to prove. Then you can prove that phi mu of phi tilde mu of f Gn minus lambda Gn. Okay. This norm 2 will go to 0, I think. But you have to prove the other way also. So suppose, so that will imply that lambda is an eigenvalue. Right? Anyway, we have proved the other way. This I will leave it. Maybe I will give it as an assignment. Okay? So since I'm not able to do now, so this is the assignment. Prove that this spectral radius of this is equal to this, okay, at n. Shall I write it? And you will note it. The spectral radius of pi mu of f is same as, it is a good exercise. Okay. I mean, it's not difficult. Okay. Just need some private space. Huh? The exercise is spectral radius of f for f in L infinity is same as spectral radius of pi mu of f. It's just multiplication operator and infinity. Operator and infinity. F is in L infinity. Mu is a measure. Multiplication operator and L2 mu. Okay. So we were into different words. We were discussing that basically. Multiplication representation of L infinity. Eh? No, this is not. We are proving that injective homomorphism of C-star algebra that preserves the norm. Homomorphism will be contractive. Why does it preserve the norm? Injective homomorphism. Yeah. That's true. But you need to use Gelfand theory and other things. So yeah. So we are directly proving it. That will involve this anyway. That proof will involve spectral radius. Huh? No. It will use the Gelfand transform. It will use the spectral radius. How will it not use that? Exactly. It does not use this particular. No. The general theory will precisely use the spectral radius formula. Okay. I mean, you will use x star x or something. You want to prove that it preserves the norm. So you will consider x star x instead of x, which is normal. Okay. So for this is equal to the spectral radius of x star x. So and spectral radius is preserved under that. See, that's the idea. I mean, because homomorphism will take invertible element to invertible element. When it is injective, it's precisely that. Maybe that itself gives here, right? So this is anyway true. I'm sorry, we don't need it. See, I mean, this follows. If you have an injective homomorphism, okay. Yeah, as he has pointed out, this is anyway direct. You don't need all that. If you have any homomorphism, if you have phi is a homomorphism from A to B, okay. If it is invertible, it will preserve the norm. Okay. I think if it is injective also. I mean, so injective means if it is invertible here, it will be invertible there. And same if it is invertible here, I mean, if the range is something is invertible, it will be invertible here. Okay. So the spectrum will be taken to spectrum. Okay. I mean, so the spectrum radius will be same. So that implies the norm is same. I don't know whether this is required. This thing. So anyway, we have proved directly the isometry part there. Maybe you don't do it as a thing. But it's an interesting thing to do. L infinity and all that. So okay. So and the last part is just a dominated convergence theorem. Last part says that, did I erase it? Yeah, I erased it. If you have Gn contained in L infinity, okay, and supremum over n of Gn is less than infinity, then pi mu of Gn converges to, and Gn converges to G almost everywhere. You have a uniformly bounded sequence such that Gn converges to Z, then pi mu of Gn converges to pi mu of Z in strong topology. Okay. But that is just, I mean, supremum, this you call it K or something, that K equal to supremum n norm Gn, which is a constant function, which is integrable, of course, and it's a finite measure. Mu is a finite measure. Okay. Now we want to consider pi mu of Gn. You want to consider pi mu of Gn minus pi mu of G acting on some, did I use Fn? Doesn't matter. So maybe H in L2. Okay. Okay. Gn are in L infinity. This you want to consider this norm, L2 norm. Okay. That will be just square of this, right? Gn minus G times norm H d mu, square of this. Okay. And this goes to 0. And this is uniformly bounded by one single integrable function. Right? This is k times, I mean, there is a constant k here times this, okay? Because it's uniformly bounded. It's finite measure, uniformly bounded by some function. So you can take the limit inside. I mean, you can take the limit inside. So this goes to 0. So it is just dominated convergence theorem. Okay, you know dominated very well, no? Dominated convergence theorem. So, of course, earlier in Riemann integrable, you know that uniform convergence, you can take it inside. Here, if you have integrable functions which are bounded by one single integrable function, sequence of integrable function bounded by something, then you can take the limit of integral Gn is integral of limit of G. I want to verify that pi mu of Gn goes to pi mu of G. So pi mu of Gn acting on a L2 vector goes to L2 vector. That L2 vector is H. Okay. So pi mu of Gn, pi mu of G acting on H norm L2, which is just going to be some integral, something like this. Okay. And this goes to 0. And these things are uniformly bounded by some k. So you have a uniformly bounded function, I mean, which bounds all these things. And this goes to 0, so this goes to 0. So bounded convergence theorem says that this goes to 0. Okay. So we have proved the second part also. Okay. So what we have proved, I have erased the theorem. We have the multiplication representation of L infinity, if which is isometric, and if some functions which are uniformly bounded, converging almost everywhere to something, okay, then the corresponding pi mu of Gn will converge in strong topology to the corresponding. Okay. So I want to do something more on, start on measure, convergence in measure. Since you haven't done, I will do it minutes. Actually, I want to prove this for convergence in measure. Maybe I will define it and then stop. What I will do next class, I will tell you. See, this statement, whatever I have in that, I want to prove the following. So definition, we have function fn, just measurable functions. Okay? There is nothing more. I mean, all this almost everywhere convergence is for measurable functions. Okay? There is no need for L infinity. Okay? Fn and Fn, F measurable. And of course, we have a measure space, we have a measure. Fn converge in measure to in measure. This is converging in measure. That's what it means. Okay, in measure. It's called convergence in measure. If mu of mod Fn minus F greater than or equal to epsilon goes to 0 for all epsilon. You fix an epsilon, then you have this set. Of course, by this you mean T such that F1 minus F of T less than or greater than or equal to. Okay. This goes to 0. This is convergence in measure. Okay. Then once we have convergence in measure, I want to prove that statement further. Okay. If Gn contained in L infinity and G in L infinity, okay, and norm of Gn infinity supremum is less than infinity, and Gn converges to G in measure, okay, then pi mu tilde of G converges, Gn converges to pi mu tilde of G strongly. That's what I want to do. How I will prove is, I will prove that, I mean, which is a standard fact in measure theory, but we will do it since you haven't done. If something converges in measure, then there is a subsequence which converges almost everywhere. Okay. But then subsequent converging in almost everywhere will prove this convergence by dominated. That's what we have. Okay. But then, see, there is a fact in, I mean, if you have some convergence in, see, there is a fact in, I mean, metric space. If you have a sequence whose every subsequence is a further subsequence which converges to same limit, then the sequence itself converges to that limit. Okay. Okay. So, but then that you can't apply to almost everywhere convergence. I mean, if that is true for this, then convergence measure and convergence almost everywhere will be same. But almost everywhere convergence is not given by some metric. Okay, so that will not work there. So if we have a convergence in measure, that will have a subsequence which converge in almost everywhere. That will imply that convergence, strong convergence. Okay. But this strong convergence on uniformly bounded set will be metrizable. Okay, I have to use that. Okay. But or we are working with sequence or something. Okay? We are working with sequences inside the H. So it's okay. Okay. So for that, every subsequence will have a further subsequence which converges something. That is the, I mean, actually there is no clear argument given in the book, but that is how I'm able to get it. Okay. Then we will prove it using that. We'll do it in the next class.